I've used a lot of Microsoft products. It's nice to be here. It is an Apple computer. That's all right, I'm told. So I'd like to take you on the next half hour away from familiar shores and on a little adventure, well, a great adventure actually, to find new aspects of reality. The title of this little talk is Anticipating a New Golden Age. In the 20th century, fundamental physics advanced dramatically, but most dramatically, I would say, in three sort of discrete, brief golden ages. One, around 1910, when the theories of relativity were developed, the special and general theory of relativity. Another around 1925, when quantum mechanics took form. And then a third, around 1970, when what's now called often the standard model, to make it sound boring, but what I call the core theory was developed, which is a profound theory of how matter behaves, not only how it behaves, but why it is what it is. That's proved to be extraordinarily accurate and precise, as well as complete, as in subsequent years it's been tested rigorously by physicists, experimenters, trying to poke holes in it and get Nobel Prizes for themselves by finding essentially new phenomena. But the core theory has held up extremely well to this probing and prodding. And so far, all those efforts to drag it down have only made it look better and better. However, we're not satisfied, because the equations of that core theory are not as pretty as they should be for a theory that's so fundamental. And conceptually, it leaves us with four distinct forces: the strong electromagnetic, weak, and gravitational forces that appear to be independent. We'd like to have a unified theory of nature in which there weren't four independent fundamental forces. And also, there are different kinds of matter, technically fermions and bosons, typified, if you like, by light, photons, and matter, electrons, that again appear to be very different. We'd like to have a description of the world in which there's only one thing. And the message is that we might be almost there. And that's why I anticipate that there's a new golden age. We have promising ideas for making these unifications. We've had promising ideas now for a while. The germs of these ideas were already present in the 1980s. But what's new is that now, just now, we're going to have the tool that seems to be adequate to see whether these ideas are in fact on the right track or not. This is what's called the Large Hadron Collider, or LHC. So in the next few minutes, I'd like to give you a brief tour of this tool, a visual tour mostly. So if you are in an airplane and flying over Geneva and look down, this is what you see: a kind of mystic scene on a beautiful day like this, with mountains in the background and mists appropriate to a mystic scene. This is Lake Geneva, the city of Geneva over here. And then you see something really peculiar. You see this big red circle on the ground. That's the LHC. Well, I'm kidding, of course. You don't actually see a red circle on the ground. In fact, what you see on the ground from this project is practically nothing, but that circle is the projection upwards of what's actually there, this 27-kilometer long ring underground, or about 18 miles, that's the LHC project. What's above ground is not very notable at all, a few little buildings spread over 27 over this radius. And what will happen there, first of all, this is what's inside that ring. These are, you have to imagine this going on for 27 kilometers or 18 miles. These are powerful superconducting magnets, similar to the ones you might find in a hospital if you're getting an MRI scan, but somewhat more powerful. And they're superconducting, so they have to be held at liquid helium temperatures. That's what all this stuff is, to keep the liquid helium flowing, to keep them within 3 degrees of absolute zero, so that they can function properly. This project, I think, in its scale and in its devotion to a kind of abstract goal, ideal, is our civilization's answer to the pyramids of Egypt. But much better, because it's really inspired by curiosity as opposed to superstition. It's constructed by cooperation rather than command. And its size is not just vanity, size for the sake of size. Its size is determined by what its function is. Oops. So what's going to happen there is that protons will be guided by those magnets in circular paths and accelerated so that their speeds are within 1 part in a million, 1 part in a million of the speed of light, which is the limiting speed. Protons moving that fast have enormous energy. You'll have beams moving in opposite directions, going around the ring, and at a few points, the beams will cross. There, collisions will occur, and densities of energy that were last seen when the universe was 100,000th of a second old, close to the Big Bang, will be reproduced again. And extremes of energy density that have never been probed before in a controlled laboratory setting will be created. To monitor what happens, people have built extraordinary detectors that you see here. Here are the people, to give you a sense of the scale of the thing. So it's like a cubicle 10-story building, 30 meters on a side, dense with electronics, fastest state-of-the-art electronics. Out of this will flow 15 petabytes of information per year, storing the results of collisions that look like this. That's equivalent to 500,000 telephone conversations going on all the time that have to be analyzed. So it's a job worthy of the NSA, the National Security Agency, but the information is encoded in much more obscure ways in the details of these particles, or you can also see here. These are what the results of the collisions look like. What you see is, in practice, you see as if this little bang, this recreation of the Big Bang in a very small volume for a very short time, leaves debris, and we'll try to reconstruct the basic processes that caused it And the difficulty of that is similar to trying to reconstruct what a mountain looked like by studying the result of an avalanche. We try to, but that's what these computers are going to do. The information will be fed to a new kind of computer architecture called the grid to deal with this gush of information, to analyze it. Our core theory, we believe, is so good that almost everything that occurs at this accelerator will be described by it. But 1 in a trillion or so of the events will have something fundamentally new. So we've got to find those events, which to the eye don't look very different from routine events. And the computers hierarchically try to figure out what's going on, find the needle in a haystack that's fundamentally new physics, and at the end of the day, finally a human being looks at it and tries to interpret what's going on. So that's a discussion of sort of what it is at a very nitty-gritty level, this answer of ours to the pyramids of Egypt as a physical object. But what is it for? What is it really? What is its purpose? It's actually very simple, and in a grand tradition of science. It's in a direct line of descent from Leeuwenhoek, studying with optical light, ordinary light, through his microscopes, with magnification and discovering cells inside living things, or Rosalind Franklin using X-rays and diffraction patterns and some sophisticated image processing done by Crick and Watson to figure out the structure of DNA. What this thing is, what this LHC is an ultra-stroboscopic nanomicroscope. We want to see with it distances much smaller than you can access with visible light or even X-rays. It's, even at a technical level, it's a nanomicroscope. That is, it's looking at things that are nano-micrometers in size, that kind of scale. And the action there is very, very rapid, so that it also has to have very good resolution in time. Now, to give you a sense of the sort of strange things that you can expect to see there, I'd like to show you a picture now of the deep structure of reality that we do understand at slightly larger scales than the LHC is going to probe. Now, our eyes were not evolved, or maybe designed, no, evolved, to resolve distances of the order of 10 to the minus 13th centimeters, or times of order 10 to the minus 24th seconds, the sort of time scales and distance scales involved in the structure of atomic nuclei or inside protons. But resolving those kinds of distances and times wouldn't have been of use in avoiding predators or finding new mates, finding desirable mates, the things that we were evolved for. However, now, using our noodles and the careful study of science and taking our equations that we can check in other ways seriously to reconstruct what our eyes would see if they had that kind of resolution in space and time, we can make an image. So I'm now going to show you a video of the deep structure of reality. This is what your eyes would see if they were capable of resolving 10 to the minus 13th centimeters and 10 to the minus 24th seconds. So if we can dim the lights a little, yeah, I guess I can even myself. Here it comes, brace yourself, the deep structure of reality. It looks like a lava lamp. This is computed, this is not some artist's impression, this is a computed with very elaborate calculations. A computed picture of fluctuations in the energy in gluon fields that are happening all the time and everywhere, according to our core theories, which we can check in many, many ways. So, now you've seen it. And the purpose of the LHC is to let us resolve even smaller things. So things that are blurry in this picture will come into focus with the LHC. It's a basic feature of our deepest theories of physics now, quantum field theories they're called, that for everything that exists as a particle or an element of reality, as a real thing, it also exists as a fluctuation in empty space, as a kind of so-called virtual particle that comes to be and passes away spontaneously all the time. And what you were seeing there was basically virtual gluons, the stuff that holds our quarks together and makes protons and neutrons, and is responsible for most of your mass. Those were the fluctuations in the gluon fields. But electron fields fluctuate, so you have spontaneous production of electrons and positrons, which come to be for a very short time, then annihilate each other, pass away, and so on for everything that exists. So that the LHC, by taking pictures of empty space, now experimentally, will be sampling these fluctuations and therefore taking a sample of everything that exists. So empty space has it all, but in the quantum world, to see something, we've learned, you have to disturb it, you have to interact with it in a minimal way. This was the conceptual revolution introduced by quantum theory. We came to see that you can't make observations with arbitrary precision without disturbing things. And in the deep quantum world, which we're concerned with here, so way, way subatomic, where quantum effects are dominant, you go one step further to see these things, to make the virtual particles real. In a sense, you have to create them. Or making that a little less mystical and more concrete, if you want to produce a particle of mass m, a particle whose fluctuations are very small in space and limited in time, then you must supply at least, to make it leap out from the virtual world into the real world, you have to supply at least a minimum energy E, which that particle can possibly have. Because since energy is conserved, you better supply the energy that's there at the end to start with. So to produce a particle of mass m, to produce a heavy particle, which corresponds to the very fine structure of space, you have to supply at least the minimum energy that that particle has, which is what it has if it's at rest, namely Einstein's famous m times c squared. And that's why LHC is meant to concentrate enormous amounts of energy, and why there's a premium on producing collisions that have enormous amounts of energy, so that we can make heavier particles, and so we can probe shorter distances and times. Now, sorry. So now I've given you the scientific background. Before the quiz, I think it's only fair to give a review. So now I'm going to give a review in, I hope, user-friendly video form. This will be a different perspective on the physics I just told you about.
Oh yeah.
Oh yeah.
I'm about to drop some particle physics in the club.
So we're dropping particle physics in the
The
club.
LHC is super duper fly. You know what I'm saying. Check it.
27 kilometers tunnel underground, designed with mind to send protons around.
Right.
A circle that passes through Switzerland and France. 60 nations contribute to scientific advance. Two billion protons swing round through the ring they ride, till in the hearts of the detectors that made it collide, and all that energy.
So these are real people, really at CERN, and most of it is quite accurate. You'll see.
Oh yeah.
CBC's where the antimatter's gone. Alice thinks a collision with a lead ion. CMS and Atlas are two of a kind.
Those are the big detectors.
Particles they can find. The LHC accelerates the photons in the lead, and the things that it discovers will rock you in the head. We see asteroids and planets, stars galore. We know a black hole resides in each galaxy's core. But even all that matter cannot explain what holds all these stars together. Something else remains. Dark matter interacts only through gravity. And how do you catch a particle? There's no way to see. Take it back to conservation of energy, and the particles appear clear as can be. You see particles flying in jets they spray, but you notice there ain't nothing going the other way. Say my law has just been dilated. That's what makes sense. There's gotta be another particle to make this balance, and it might be dark matter. And for the first time, we catch a glimpse of what we saw most of the known works because. CBC's where the antimatter's gone. Alice and collisions of lead ions. CMS and Atlas are two of a kind. They're looking for whatever new particles they can find. And that is sort of like matter's evil twin, because except for charge, and given this a spin, they're the same for a particle and its anti-separate. You can store an antiparticle on your shelf, because when it meets its normal twin, they both annihilate. Matter turns to energy, and then it dissipates. The matter is created from energy, which is exactly what they'll do in the LHC. You get matter and antimatter in equal parts, and they try to take this back to when the universe starts, the Big Bang. Back when all the matter exploded, but the amount of antimatter was somehow eroded, because when we look around, we see that matter abounds, but the antimatter's nowhere to be found. That's why. CBC's where the antimatter's gone. Alice thinks it collisions with lead ions. CMS and Atlas are two of a kind. They're looking for whatever new particles they can find. The LHC accelerates the photons in the lead, and the things that it discovers will rock you in the head. And the explosion, that's the one that everybody talks about. And there's no one sure thing that this machine will sort out. If the Higgs insists, they ought to see it right away. And if it doesn't, the scientists will finally say that there's no Higgs, we need no physics to account for why things have math. Something understand their model went awry. But the Higgs also have the just what it does. They suppose the particles are mass because there is this Higgs field that extends to all space. And some particles slow down while other particles race straight through like the photon. It has no mass, but something heavy like the top or extravagant. And the Higgs is the boson that carries the force. And the particles take orders from the field that is its source. They'll detect it.
Okay, now, actually this video goes wrong at that point, so I'm going to stop. But I hope you found that entertaining as a review. And now I'd like to discuss what I hope and expect will be the most profound scientific development to come out of this. So my vision. Oops. I mentioned that we have a core theory that's extremely accurate, very complete as a description of normal matter, and very precise and in its way mathematically elegant, but it still has flaws. In particular, it postulates the existence of four fundamental forces that are separate. The traditional forces of physics that have been known for hundreds of years, gravity and the electromagnetic forces, and two that were only discovered in the 20th century when we carefully studied subnuclear physics that are called the strong and weak force, not very imaginatively. Now, I'll leave gravity aside for the moment. The other three forces are described by equations that have a family resemblance. Some of you probably know that in electromagnetism we have Maxwell's equations, which are the classic equations of electromagnetism. The equations we use today in the core theory for the weak and strong interactions are kind of like Maxwell's equations on steroids. They have not one kind of charge, which is electric charge, in the electromagnetic interactions, but several kinds of charges that are called colors or weak charges in the different cases. But they really have very similar properties to electric charge. And so we have this very suggestive situation where at least three of the four fundamental forces seem to be described in very similar terms with elegant equations based on symmetry. We would like to think, it seems that nature is begging us to try to see all these different forces as aspects of one underlying, unifying structure, like different sides of a die, with all the charges being different sides of the same die. And when you try to implement that idea, you very quickly find some striking successes. Things you didn't understand before suddenly make sense in that context. I told you the equations of the core theory are somewhat lopsided. If you embed them in a larger structure that makes symmetry between the different kinds of charges, then you learn that they're lopsided in just the way they had to be in order for them all to fit on the same die, roughly speaking. Or another way of putting it is if they weren't lopsided in exactly the way they are, but a different way, it wouldn't work. So that's understanding why they're lopsided in the particular way they are. So a lot of things work. You explain more things. You explain more that you didn't understand before. However, one thing doesn't work. If there's going to be a way of seeing all these different interactions on the same footing, putting them into a unified field theory, they have to have the same basic power. But when we go out and observe, we find that they don't have the same basic power. The strong interaction really is stronger, even at the shortest distances we've measured, than the other interactions. So if we put strength of interaction this way, it's on the bottom, and then the other interactions are like that. However, now we remember, and another problem with the standard model as a final theory of nature is that we're left with different kinds of matter. We would like to think there's not only just one underlying interaction, but also one kind of matter. But in the theory, there are four different kinds of matter. I'm simplifying a bit. Where it says electrons, it should say leptons, for instance, but never mind. But basically, there are four distinctly different kinds of matter: electrons and quarks, photons, and gluons, that are the building blocks of normal matter. And 4 is a pretty small number, but 1 is even smaller. We'd like to get to complete unity. So now our vision of unity almost works, but it doesn't. So we could give up, but rather than giving up, we remember that what we see isn't necessarily what there is. We don't see right down to the shortest distances where presumably the simplest, most basic properties are revealed. We see through this distorting medium of fluctuations. And so if we're going to really see what's basically there at the shortest distances, it gets it all started, we have to strip away the distortions introduced by this medium we're embedded in. And although it's very difficult to do that experimentally, I showed you how to get to shorter distances by a factor of 10, you have to build the LHC. If we want to get many orders of magnitude, which is what's required here, we'd have to build a super LHC that circled the Earth, or maybe one that filled the orbit of Pluto or something like that. And that's not going to happen anytime soon. But using our noodles, we can calculate what happens. And when we do that, when we make this correction, we find a wonderful result. I was going to say surprise. It certainly was a surprise when I first found it, but now it's a result. That is that, lo and behold, when we do the corrections, strip away those distortions, they do come together. And so the differences between electrons and quarks, which followed from the fact that they have different strong and weak electromagnetic and weak interactions, fall away if those interactions all are seen as part of an underlying unity. So that's unified. And these guys gets unified too. However, there was an asterisk, which now I'm going to own up to. The asterisk is that in doing this calculation of the distortion, I had to include all the fluctuations that exist. And when I did that, using just the particles we know about, it didn't quite work. It does work, however, if we up the ante a little bit, expand our equations in another direction, we didn't have complete unity. Sorry. We didn't have complete unity before because the different kinds of matter still fell into 2 bits. There's room for expanding the equations further to making complete unity among different kinds of matter. This, to a physicist, at first seems completely outrageous because electrons and photons are such different kinds of particles. How could they be seen as different aspects of the same underlying reality? Electrons repel each other by what's called the Pauli exclusion principle. They refuse to do the same thing in quantum mechanics. Whereas photons love to do the same thing. That's why they organize themselves into laser beams and so forth. So they're as different as can be. These are called fermions and bosons. But there is a way, it's called supersymmetry, of embedding them in a set of equations where they appear on the same footing and symmetrically. That requires expanding the equations of physics, adding new stuff. When we add new stuff, that new stuff appears as virtual particles and contributes to the correction. And so when I did the calculation of the correction that actually worked, that was including the extra stuff you needed to get supersymmetry. So by upping the ante to get unification in both directions, it finally works. And as a bonus, well, it works, but the particles had better show up at the LHC. And as a bonus, I left gravity to the side. Now I'm going to bring it back. Gravity, as a force between elementary particles, is ridiculously weaker than the other forces. You see here, the strong force is about 10 times stronger than the electric force, for instance. If I tried to put gravity on the same footing, it would not be just 10 times weaker, or not 10 times 10, imagine going up, or 10 times 10 times 10. You would have to multiply by 10 41 times until you got to gravity. That would take you way, way, way outside the known universe. So gravity is ridiculously weaker technically by a factor of 10 to the 41 than the other forces. It wouldn't fit here. It would go way, way outside the known universe. However, gravity responds directly to energy, and so its effective strength is not just modified by these fluctuations in empty space, but also just by the fact that at short distance you have larger energies in the fluctuations. And gravity also has to be modified. The measure of its strength is also modified as you go to short distances or large energies. You can do the calculation to compare. I've done it. So here it comes. Gravity, from being way, way outside the known universe, at the last minute comes and unifies pretty much with the other ones too. So it's a really tantalizing vision, I think, of upping the ante for unification in two very different senses, and then everything really clicks together. So nature is singing a siren song. Is she teaching or teasing? I don't know. But here I am, having listened to the siren song, finally getting to confront nature. And there's going to be, at the LHC, a trial by fire. Because those particles that we needed to make it all work, these particles associated with supersymmetry, will either show up or not. And if they don't show up, the trial by fire will annihilate the whole thing. The ideas will go up in smoke. But on the other hand, maybe this will happen. You analyze these events. Oh, there's a supersymmetric particle. And there's another one. So we're going to find out. Before very long, the time scale is maybe 1 year, maybe 5 years, whether these tantalizing visions of unification and a new golden age of physics correspond to reality or not. So, thank you very much for your attention.